Hello and welcome to lecture number 4 in the course Computer Graphics. Before we start, we will briefly recap what we have discussed in the previous lectures. So, we started with a basic introduction to the field, where we discussed about the historical evolution as well as the issues and challenges that are encountered by the workers in this field. This was followed by a basic introduction to the graphics system. So, whenever we talk about computer graphics, implicitly we refer to some hardware platform on which some software works, and the basic hardware structure or architecture of a graphics system has been introduced in one of the previous lectures. Today, we are going to introduce the other component of a graphics system, namely the graphics software. Of course, at this stage we will restrict ourselves to a basic introduction, and the software stages will be discussed in details in the subsequent lecture. So, let us recap what we have learned about a generic architecture of a graphics system. As we mentioned in one of our earlier lectures, so there are three unique components of a graphics system. One is the display controller, one is the video memory, and the third one is a video controller. What the display controller does? It essentially takes input from the host computer as well as from some external input devices which are used to perform interactive graphics, and based on that input it creates a representation, a digital representation of a 2D image. So, that is the job of the display controller. Now, that representation that the controller generates is stored in a memory which is called video memory. Now, the content of the memory, video memory, is given as input to the third component, that is the video controller, which takes the memory content as input and then generates certain voltage levels to drive some electromechanical arrangements that are required to ultimately display the image on a computer screen. As you may recollect, we also mentioned that most of the things are done separately without involving the CPU of the host computer. So, typically computers come with a component which is called graphics card, which probably all of you have heard of, which contains the video memory, the video controller and the display controller components. And the processing unit that is typically part of the display controller is known as the GPU or graphics processing unit. This is separate from the CPU or the main processing unit of a host computer, and the GPU is designed to perform graphical activities, graphical operations. Now, in this generic architecture, as we said, display controller generates representation of an image. So, what that representation contains? It contains some color values or intensity values in a specific format, which ultimately is used to generate the particular sensation of color on the screen. Now, from where these color values are obtained? Let us try to go into some details of the process involved in generating these color values. Now, these color values are obtained by the display processor through some computations that are done in stages. So, there are a series of computations, and these computations ultimately result in the generation of the color values. Now, these stages or the series of steps that are involved in the generation of color values are together called the graphics pipeline. This is a very important terminology, and in our subsequent lectures we will discuss in details the stages of the pipeline. That actually will be the crux of this course. But today we are going to introduce the pipeline for our benefit, so that we can understand the later discussion better. So, let us get some introductory idea on the pipeline and its stages. There are several stages, as I mentioned. First stage is essentially defining the objects. So, when we talk of creating a scene or an image, it contains objects. Now, there needs to be some way to represent these objects in the computer. That activity where we define objects which are going to be part of the images constitute the first stage of the pipeline, which is called object representation stage. For example, as you can see in this figure on the screen, we want to generate the image of a cube with color values as shown on the right hand part of the screen. Now, this image contains an object which is a cube, and on the left hand side here we have defined this cube. So, when we talk of defining, what we mean essentially, as we can understand intuitively, defining a cube involves specifying the vertices or edges with respect to some reference frame. That is the definition in this simple case, that is, what are the vertices or what are the edges as pair of vertices. Of course, cube is a very simple object. For more complex objects, we may require more complex definitions, more complex way of representing the objects. Accordingly, several representation techniques are available for efficient creation and efficient manipulation of the images. Note here on the term efficient. So, when we talk of this term efficient, essentially what we refer to? We refer to the fact that the displays are different, the underlying hardware platforms are different. So, whatever computational resources we have to display something on a desktop or a laptop are likely to be different with respect to whatever we have to display something on a small mobile device or on a wearable device screen. Accordingly, our representation techniques should be able to utilize the available resources to the extent possible and should be able to allow the users to manipulate images in an interactive setting. So, the efficiency is essentially with respect to the available computing resources and the way to make optimum use of those resources. Now, once we define those objects these objects are then passed through the subsequent pipeline stages to get and render images on the screen. So, the first stage is defining the objects, and in the subsequent stages we take these object definitions as input and generate image representation as well as render it on the screen. What are those subsequent stages? First one is modeling transformation, which is the second stage of the pipeline. Now, as I said, when we are defining an object, we are considering some reference frame with respect to which we are defining the object. For example, the cube that we have seen earlier. To define the cube, we need to define its coordinates, but coordinates with respect to what? There we will assume certain reference frames. Now, those reference frames with respect to which the objects are defined are more popularly called local coordinate of the object. So, the objects are typically defined in their own or local coordinate system. Now, multiple objects are put together to create a scene. So, each object is defined in its own or local coordinate system, and when we are combining them, we are essentially trying to combine these different reference frames. By combining those different objects, we are creating a new ensemble of objects in a new reference frame, which typically is called world coordinate system. Take the example shown on this figure. So, here as you can see, there are many objects, some cubes, spheres and other objects, cylinders. Each of these objects is defined in its own coordinate system. Now, in this whole scene consisting of all the objects, this is the whole scene. Here we have assembled all those objects from their own coordinate systems, but here again we are assuming another coordinate system in terms of which this assembling of objects is defined. So, that coordinate system where we have assembled them is called the world coordinate system. So, there is a transformation, transforming an object from its own coordinate system to the world coordinate system. That transformation is called modeling transformation, which is the second stage of the graphics pipeline. So, in the first stage we define the objects, in the second stage we bring those objects together in the world coordinate system through modeling transformation, which is also sometimes known as the geometric transformation. So, both the terms are used, either modeling transformation or geometric transformation. That is the second stage of the graphics pipeline. Now, once the scene is constructed, the objects need to be assigned colors, which is done in the third stage of the pipeline called lighting or illumination stage. Take for example, the images shown here. In the left figure we have simply the object, in the right figure we have the colors. So, we have applied colors on the object surfaces. Now, as you can see, the way we have applied colors, it became clear which surface is closer to the viewer and which surface is further. In other words, it gives us a sensation of 3D, whereas without colors like the one shown here, that clarity is not there. So, to get a realistic image which gives us a sensation of 3D, we have to assign colors. Assignment of colors is the job of the third stage, which is called lighting or illumination stage. Now, as probably you are aware of, color is a psychological phenomenon, and this is linked to the way light behaves, or in other words, this is linked to the laws of optics. And in the third stage, what we do? We essentially try to mimic these optical laws. We try to mimic the way we see color or we perceive colors in the real world, and based on that we try to assign colors in the synthesized scenes. So, first we define an object, second we bring objects together to create a scene, third stage we assign colors to the object surfaces in the scene. Now, till this point everything we were doing in 3D setting in the world coordinate system. Now, when we get to see an image, the computer screen is 2D. So, essentially what we require is a mapping from this 3D world coordinate scene to 2D computer screen. That mapping is done in the fourth stage, that is viewing transformation. Now, this stage we perform several activities which is similar to taking a photograph. Consider yourself to be a photographer. You have a camera and you are capturing some photo of a scene. What you do? You place the camera near your eye, focus to some object which you want to capture, and then capture it on the camera system, and also this is followed by seeing it on the camera display or camera screen if you are having a digital camera. Now, this process of taking a photograph can be mathematically analyzed to have several intermediate operations, which in itself forms a pipeline, which is a pipeline within the broader graphics pipeline. So, the fourth stage viewing transformation itself is a pipeline which is a part of the overall graphics pipeline. Now, this pipeline where we transform a 3D world coordinate scene to a 2D view plane scene is called viewing pipeline. Now, in this pipeline what we do? We first set up a camera coordinate system, which is also referred to as a view coordinate system. Then the world coordinate scene is transformed to the view coordinate system. This stage is called viewing transformation. So, we have set up a new coordinate system, which is a camera coordinate system, and then we transform the world coordinate scene to the camera coordinate scene. From there we make another transformation. Now, we transform the scene to a 2D view plane. Now, this stage is called projection transformation. So, we have viewing transformation followed by projection transformation. For projection, we define a region in the viewing coordinate space, which is called view volume. For example, in the figure shown here, as you can see, this frustum is defining a view volume. The frustum shown here is defining a view volume. So, we want to capture objects that are present within this volume. Outside objects we do not want to capture. That is typically what we do when we take a photograph. We select some region on the scene and then we capture it. So, whichever object is outside will not be projected and whichever are there inside the volume will be projected. So, here we require one additional process, a process to remove objects that are outside the view volume. Now, those objects can be fully outside or can be partially outside. So, in both the cases we need to remove them. So, when an object is fully outside we completely remove it, and when an object is partially outside we clip the object and keep only the part that is within the view volume, the outside part we remove. The overall process is called clipping. Also, when we are projecting, we consider a viewer position, where the photographer is situated and in which direction he or she is looking at. Based on that position, some objects may appear fully visible, some may appear partially visible, whereas the other objects will become invisible. But all of them may be within the same volume. For example, with respect to this particular view position, some objects may get like this object. If it is behind this object, then it will be invisible. If it is partially behind, then it will be partially visible, and if they are not aligned in the same direction, then both of them will be fully visible. So, we take care of this fact also before projection, which requires some further operations, computations. So, to capture this viewing effect, the operations that we perform are typically called hidden surface removal operations, or similarly visible surface detection operations. So, to generate realistic viewing effect along with clipping, what we do is we perform the hidden surface removal or visible surface detection operations. So, after clipping and hidden surface removal operations, we project the scene on the view plane, that is a plane defined in the system, in the view coordinate system. Now, there is one more transformation. Suppose in the right hand figure, suppose this is the object which is projected here in the view plane. Now, the object may be displayed on any portion of a computer screen. It need not be exactly at the same portion as in the view plane. For example, this object may be displayed in a corner of the display. So, we will differentiate between two concepts here. One is the view plane, which is typically called a window. Other one is the display region on the actual display screen, which we call viewport. So, one more transformation remains in the viewing pipeline, that is transferring the content from window to the viewport. So, this is called the window to viewport transformation. So, in summary, what we can say is that in the fourth stage there are three transformations. What are those transformations? First, we transform from world coordinate scene to camera or view coordinate scene. Then from camera coordinate scene we perform the projection transformation to view plane. Then the view plane window is transformed to the viewport. So, these are the three transformations. Along with those, there are two major operations that we perform here. One is clipping, that is clipping out the objects that lie outside the view volume, and the other one is hidden surface removal, which means creating a realistic effect, viewing effect with respect to the viewer position. So, that is the fourth stage. So, first we defined objects in the first stage. In the second stage, we combined those objects in a world coordinate scene. In the third stage, we assigned colors to the object surfaces in the world coordinate scene. In the fourth stage, we transformed the world coordinate scene to the image on the viewport through a series of transformations which form a sub pipeline within the overall pipeline. And those sub pipeline stages are viewing transformation, projection transformation, and window to viewport transformation. This sub pipeline is called viewing pipeline, which is part of the overall graphics pipeline. And in the fourth stage, along with this viewing pipeline, we also have two more operations performed, that is clipping and hidden surface removal. One more stage remains, that is the fifth stage, which is called scan conversion or rendering. Now, we mentioned earlier that we transform to a viewport. Now, viewport is an abstract representation of the actual display. In the actual display, if you recollect our discussion on raster displays, we mentioned that the display contains a pixel grid. So, essentially the display contains locations which are discrete. We cannot assume that any point can have a corresponding point on the screen. For example, if in our image we have a vertex at location 1.5 and 2.5, on the screen we cannot have such a location, because on the screen we only have integer values as coordinates due to the discrete nature of the grid. So, we can have either a pixel located at 2, 2 or 3, 3 or 1, 1 or 1, 2, something like that, rather than the real numbers 1.5, 2.5. So, we cannot have a pixel location at say 1.5, 2.5, but we can have pixel locations only at integer values say 1, 1, 2, 2 and so on. So, if we get a vertex in our image located at 1.5, 2.5, then we must map it to these integer coordinates. That stage where we perform this mapping is called the scan conversion stage, which is the fifth and final stage of the pipeline. For example, consider this line shown here. The endpoints are 2, 2 and 7, 5. Now, all the intermediate points may not have integer coordinate values, but in the final display, in the actual display, we can have pixels, these circles only at integer coordinate values. So, we have to map these non-integer coordinates to integer coordinates. That mapping is the job of this fifth stage or scan conversion stage, which is also called rasterization. And as you can see, it may lead to some distortion, because due to the mapping we may not get the exact points on the line. Instead, we may have to satisfy ourselves with some approximate points that lies close to the actual line. For example, this pixel here or this pixel here is not exactly on the line, but the closest possible pixel with respect to the line. So, what is the concern? How to minimize the distortions. Now, these distortions has a technical name which is called aliasing effect. From where this name originated, we will discuss later. So, our concern is to eliminate or reduce the aliasing effect to the extent possible, so that we do not get to see too much distortions, we do not get to perceive too much distortions. To address this concern, several techniques are used which are called anti-aliasing techniques. These are used to make the image look as smooth as possible to reduce the effect of aliasing. So, let us summarize what we have discussed so far. We mentioned the graphics pipeline. It contains the 5 stages. First stage is object representation, second stage is modeling transformation, third stage is assigning colors or lighting, fourth stage is the viewing pipeline, which itself has a sub pipeline involving viewing transformation, clipping, hidden surface removal, projection transformation and window to viewport transformation. And the final stage is scan conversion, which is the 5th stage. So, there are broadly 5 stages involved. Now, each of these stages has its own reference frames, own coordinate system. So, in stage 1 we deal with local coordinate system of the objects. In stage 2 we deal with world coordinate system. So, essentially we transform from local to world coordinate system. Stage 3 we deal with again world coordinate. So, when we are assigning colors, we are essentially assuming that the objects are defined in the world coordinate system. In stage 4 again different coordinates are used. So, first transformation, that is viewing transformation, involve transformation from world coordinate to view coordinate system or the camera coordinate system. Clipping is performed on the view coordinate system. Hidden surface removal is also performed in the view coordinate system. Then we perform a transformation, projection transformation, which transforms the content of the view coordinate system to a 2D view coordinate system. So, we have 3D view coordinate system, from there we transfer the content to a 2D view coordinate system. And in the window to viewport transformation, we transfer from this 2D view coordinate system to device coordinate system. And finally, in the 5th stage, what we do? We transfer from device coordinate to actual screen coordinate system. Note that device coordinate is an abstract and intermediate representation, whereas the screen coordinate is the actual pixel grid. So, device coordinate contains continuous values, whereas screen coordinate contains only discrete values in the form of a grid. So, this is in summary what is there in the graphics pipeline. So, display controller actually performs all these stages to finally get the intensity values to be stored in the frame buffer or video memory. Now, these stages are performed through software, of course with suitable hardware support. For a programmer of a graphic system, of course, it is not necessary to learn about the intricate details of all these stages. They are quite involves lots of theoretical concepts, lots of theoretical models. Now, if a graphics programmer gets bogged down with all these theory models, then most of the time will be consumed by understanding the theory rather than actually developing the system. So, in order to address this concern of a programmer, what is done is essentially development of libraries, graphics libraries. So, there is this theoretical background which is involved in generating 2D image. the programmer need not always implement the stages of the pipeline to fully implement the theoretical knowledge. That would be of course too much effort, and major portion of the development effort will go into understanding and implementing the theoretical stages. Instead, the programmer can use what is called application programming interfaces or APIs provided by the graphics libraries, where these stages are already implemented in the form of various functions, and the developer can simply call those functions with arguments in their program to perform certain graphical tasks. There are many such libraries available. Very popular ones are mentioned here: OpenGL, which is an open source graphics library which is widely used. Then there is DirectX by Microsoft, and there are many such other commercial libraries available which are proprietary, but OpenGL being open source is widely accessible and useful to many situations. Now, what these libraries contains? They contain predefined sets of functions which, when invoked with appropriate arguments, perform specific tasks. So, the programmer need not know every detail about the underlying hardware platform, namely processor, memory and OS, to build a application. For example, suppose we want to assign colors to an object we have modeled. Do we need to actually implement the optical laws to perform the coloring? Note that this optical law implementation also involves knowledge of the processors available, the memory available and so on. So, what we can do is, instead of having that knowledge, we can simply go for using a function GL color 3F with an argument RGB. So, this function is defined in OpenGL or the Open Graphics Library, which assigns a color to a 3D point. So, here we do not need to know details such as how color is defined in the system, how such information is stored in which portion of the memory and accessed, how the operating system manages the call, which processor, CPU or GPU handles the tasks and so on. So, all these complicated details can be avoided, and the programmer can simply use this function to assign color. We will come back to these OpenGL functions in a later part of the lecture, where we will introduce OpenGL. Now, graphics applications such as painting systems, which probably all of you are familiar with, CAD tools that we mentioned in our introductory lectures earlier, video games, animations, all these are developed using these functions. So, it is important to have an understanding of these libraries if you want to make your life simpler as a graphics programmer, and we will come back later to these library functions. We will discuss in details some functions popularly used in the context of OpenGL. So, in summary, today we have learned some idea of 3D graphics pipeline and also got some idea, introductory idea to the graphics libraries. In subsequent portion of the course, we will discuss in details all these stages as well as some more details of the graphics libraries and the graphics hardware. That is all for today. Whatever I have discussed today can be found in chapter 1 of the book mentioned here, you are advised to refer to section 1.4 and 1.5. Thank you and goodbye.